Okay, so again, we're starting on page 55. But right now, we'll take our look at the calendar. Last class, we introduced exponential functions. That's what part of this quiz was on. Today, we talk about exponential models, that is, applications of exponential functions. We saw one application last class, and that was the drug filtration stuff. It turned out that if your body can process and get rid of 25% of the drug that's in your system at any moment in time, then that's an exponential decay thing. And we looked at the graph, and we found an equation. We'll do more stuff with models today, and also this special number E. Then on Wednesday, we review for test number 3, which is happening Friday. Any questions on any of that? Okay, then let's go ahead and take a look on page 55. Page 55 works through this concept of compound interest. So for example, if you have $100 in a bank account and it earns 10% interest per year, how much interest do you get at the end of that year? $100 at 10%, you get $10, right? But in reality, you're probably going to get more than $10 because you're not just going to get interest once at the end of 12 months. You'll probably get interest like every month, like a little bit every month. And the reason that that it works out to be more than $10 at the end of the year is that the little bit of interest you earn in January starts to earn interest for you as soon as you get it at the end of January. And so then what you get in February is going to be a little more than what you got in January. And then in March, you have interest on January's interest plus February's interest. And so March will be even greater than the gain that you had in the previous month. We're probably not talking a whole heck of a lot of a difference, but you know, it's better for you the more often you compound interest, the more often you get the interest. So part of the reading from last night, which is in the packet, works through that. But because we took a little extra time on the quiz, I'm just going to jump to the formula, and you can read through it and ask me questions later on if you want to. But let's go to the next page, which unfortunately the number is blocked off, but it's page 56. And we're going to use this crazy formula here in number 5. So here's the basic idea. You start with a certain amount of money called P for what word? Principal. You start with the principal. You invest that in a bank account. What is R supposed to represent? The rate, interest rate. Always as a decimal. Don't put 7% up there. Put 0.07. You're going to let that money grow for T years. And then the only other thing in this formula is this funny N. And N is the new piece. N is how often you get interest every year. So if I say you get interest compounded monthly, then how many times do you get interest during the year? 12 times. N would be 12 if I said monthly. What if I said every week you get interest? How much would N be? 52. 52 times a year, 52 weeks in a year. If I said you get interest once at the end of every day, how much is N? 365. If I say you get interest once every quarter, how many quarters are there in the year? There are 4 quarters in the year. January through the end of March is the first quarter. It's like a business term. So N is how many times the interest is compounded each year. And then finally, this whole A of T business is just how much money is in your bank account after T years. Okay, so that's generally what we're after is figuring out how much money you have in your account. So let's try number 6. We'll go to Taylor.
What is the value of $100?
Okay, so let's just see if we can find where all these pieces go. So we're going to start here with P. How much is P? 100, right? It's the principal. Times 1 plus somebody we haven't heard from. What do I put for R? We put 10. 0.10. Make sure we put a decimal up there. We get 0.10 divided by, if we're compounding quarterly, then how much is N? 4, right? 4 quarters in the year. How much is the N up there? Also 4, same N. T is how many years you're getting interest. How much is T in this problem? 1 year. That's how long we're going to let the money grow. And then we're just going to type all of that in. We can call it A. More specifically, it's A of 1 year that we're finding. And we're going to get a number for this, and it's going to represent how much money we have. Before we type it into the calculator, just pause for 1 second. Suppose it was $100 at 10% just once, how much money will you have at the end of the year if you get 10% interest one time? You have $110, right? Is this number, when we plug in the 4, going to be more or less than 110? A little bit more. Maybe 111, maybe 112. I'd be surprised if it was 115, right? It's not going to be a lot more than 110, but it should be something a little more than 110. So we'll very carefully type this thing in. We'll do it here. So we're doing 100, parentheses 1 plus 0.10 divided by 4 raised to the 4 times 1. A little more than 110 is what we're expecting. Not a lot more than 110. So that extra compounding earned you a whopping 38 cents at the end of the year. Yeah, Matt. You have to close the 1/4 parentheses before you raise it to the 4th power. You need another. You have an extra parentheses that I don't, so you need to close it. Any other problems typing this in? Okay, so is 38 cents a big deal? Probably not, but if this is millions of dollars, which it might be for like big companies or for countries for that matter, then that would be a big deal, right? Okay, what if we try the same thing for 3 years? So all this stuff is the same, but now we're plugging a 3 for what number? I wouldn't say we're plugging it for A, for T. Okay, so 100, 1 plus 0.1 over 4 to the 4 times 3 years. Okay, so I'll just do second enter, and then I'll just change my 1 to a 3. Now before I hit enter, suppose it was just 10%, forget the compounded quarterly. 10% in 1 year gives you how much interest? $10. In the second year, I'll probably get a little more than 10, like $11, but basically $10 a year for 3 years. So I'm expecting a number something like about $30 more, maybe 34. Did you say 30 or 40? 30-ish, 40-ish, something like 1,000 and like another $30 and change. Is that what I get? Oh, I like this bank account. That's good. No. Yeah. Okay, now I like this bank account. Right? That's a whole lot better than the $130 we were expecting. Is that right? After 3 years, 10% interest, and we gained, gosh, $231. That's pretty good. Like tripled our money and then some. Is this right? Eric says we were expecting $130, maybe $140. Is this right? That's not right. We want it to be right. I typed it in wrong. What did I forget to put in? The 0.10 over 4 is not the problem. Four times 3. You and I all know that 4 times 3 is the exponent because that's what it looks like in purple when we write it. The calculator doesn't know that. The calculator thinks I'm doing a 4th power, no problem, and then times 3 bank accounts. That's why it's big. So if we put in parentheses, Eric, what were you expecting? About 130-ish, 140-ish. Perfect. It's really easy to get the wrong answer and not catch it if you're not thinking about what it should be, right? So don't just mindlessly type stuff in, but I would like to make sure that you know how to type stuff in. Any questions on that one? So we'll say 134 and 49 cents. All right, any questions on that? Okay, another question that maybe we'd like to know the answer to. Suppose that we have a, like how much does like a Wii cost? 300? 200? Okay, suppose that we have our eye on this Wii and we'd really like to buy it, but we have only $100 right now. And so we're gonna throw it into the bank. And what's the question we're gonna ask? How long will it take? How long will it take for my $100 to grow to $200 so I can go kill my brain cells with the video games. I'm sorry, I editorialized there. I like video games. So that's the question, right? How long? All right, if we're answering a how long question, then I feel like we're making some slight changes to this equation. If I say how long, it's still 100, it's still 1 plus 0.10 over 4, it's still a 4, but what goes up there now is times t, to be determined. What goes on the other side of the equals? Is that $200? That's how much I want the money to grow to. So that's the equation we'd like to be able to solve. If you can find t, you know how long it's going to take before you can buy your video game system. Where's the variable? It's in the exponent. We have never solved an equation algebraically where the variable's in the exponent. We're going to have to wait until after the test, and we're going to come up with this tool called logarithms. So we can't answer that question yet, but we will soon enough. Right? Let's move on to a different kind of question. Number 7. Did we have a reader yet? Not yet. Oh yeah, we did. Taylor. Michael, number 7. Okay, let's see if we can figure out what's happening here. How much is P in this example? $1. We're going to put $1 into the bank. We're going to let it grow at 100% interest. So how much will it become at the end of a year? You start with $1 and you gain another 100%, another $1, you'll have $2, right? If you gain 100%, you're going to end up with double what you started with after a year. But that's assuming you only get that money once. The interest only gets to you one time at the end of the year. But now we're going to let it go n times. So maybe I'll give you interest. We're on page 57, 56 doesn't really have a number. So here's the question. If you get interest just once at the end of the year, how much will you have total? $2. Okay. What if I give you interest maybe once in the middle of the year and then once at the end of the year? Will you have more or less than $2? A little bit more. What if I give you interest every month? Then a little more still. What if I give you interest every day? A little more still. Every second, I'm going to fling like a little fraction of a penny your way. And you're going to end up with a little bit more money than you had if I just gave it to you every day. So here's the question. What if I had just all the time in the world and I could like continually pelt you with these little penny atoms, like all the time, more often than every second, right? Like every millisecond, and even more often than that. How much might you end up with? We know we're starting with $2. We're going to get more than that. Could you get $3 at the end? Could you get $5? Could you get a gazillion dollars if I just give you interest fast enough, often enough? That's the question. The answer is no. You can't get a gazillion dollars. First of all, that's not a number. Second of all, if you take a look at this table, the right-hand column is telling you how much you'll have in the bank at the end of the year. The left-hand column is how often you get interest. So if I just give you interest once at the end of the year, how much do you have at the end? $2. We saw that. If we do 5 times a year, then you'll have about $250. Great. That's even better. If I give you interest 100 times a year, you'll have $270 and change. Here's where problems start to happen. If I give you interest 1,000 times a year, I'm only really giving you like an extra penny. If I give you interest 10,000 a year, now I'm not even giving you a full penny. I'm giving you like 2/10 of a penny. If I give you interest 1,000,000 times a year, these little fractions of a penny, I'm going to give you 1,000,000 of them during the year. You're still only at $2.71 and change. And you can look at the difference between that number and that number. It's hardly anything. So are we going to get to a gazillion dollars? No. We're not even going to get to $3. It's counterintuitive. It feels like the more often you get interest, the more money you should make. And it's true. But it doesn't. Yeah. Yeah. And it just doesn't grow without limit. It grows. Every number is bigger than the one above. But it doesn't grow to infinity. It's got a cap. Yeah, and this idea of rate of growth is a calculus thing. And so there is a calculus thing happening here. But it turns out that the limit is right around $2.72. And in fact, you won't even get to $2.72. It's still less than that. But that number right there, this number that we're tending towards is a special number. And we're going to go down here to number 9. Who's our reader now? Brian? all of that. So what does E represent? E represents how much money you'll have in the bank after 1 year if you start with $1 and you compound at 100% interest more and more often. How often? Infinitely often. More than 1,000,000 times a year. Every moment of the year, I'm going to give you a little atom of a penny. And at the end of the year, you're going to have E dollars, $2.71 and change. Okay. Where else have we named a number in math before? Pi. Pi is like the most famous letter that represents a number, right? That 3.14, all that stuff. It's important enough to give a letter to. We call it pi. This number right here is important enough to give a letter to. We call it E. It's on your calculator. Can you guys find a button that says E in yellow? See it right above the division symbol? If I do second and then E, it says, okay, E. And if you hit equals, what does it say? It says that guy. Okay. The calculator knows what E is. 2.718, 2.7. That's all I'm asking for you guys. It's 2.7 and change. It goes forever. If you have a lot of time, I guess you can memorize a bunch of digits, but 2.7 is good enough. All right, so then what if I wanted to know how much E squared is? Ballpark? 2.7 squared? Definitely less than 9, right? That's 3 squared. How about 2 squared? More than 4. Okay, something between 4 and 9. That's good enough. The calculator can do it. One thing, if I wanted to do, for example, E to the 3rd power, then I could type it in and I'll get something, you know, like 20-ish. Great. But if I, hey, 20-ish, that's pretty good, right? But if I wanted to do that, there's actually another place, because raising E to a power turns out to be really, really common enough that we actually have a button that says E to the. It's right above the ln on the left-hand side. See that one that says E to the x? So you push one button for E to the x, then you push the 3. And it takes care of it. And like I said, it happens so often that we give it another button. Okay? So either way is fine, but I'm going to be using the one on the left. All right, let's go to this natural stuff. Katrina. Okay, so let's take a look at these graphs. So you got the lower blue one is y equals 2 to the x. 2 to the x, we have seen exponential growth things before. How do you know that 2 to the x is a growth and not a decay? Why? Because a is bigger than 1. You guys remember? Whatever that number is, 1 is the magic cutoff. If you put a number more than 1, grows. Put a number between 0 and 1, shrinks, decays. Okay, so 2 to the x is that one. 3 to the x is this one. You can see it's growing a little bit faster than the other one. It's just a little bit above, right? At every moment, you pick a point, and 3 to the x is higher than 2 to the x. Great. Why does that purple one make sense for this e to the x? I'm telling you that's the purple. Why does it squeeze between? Because it's 2.7. That's what e is. So if I say 2.7 to the x, well, sure, it's going to be between 2 to the x and 3 to the x. So e to the x just sneaks in between. Which one is it closer to? The 3, of course. 2.7 is closer to 3 than it is to 2, all right? Okay, it is called the natural exponential function, as opposed to just any old exponential function, because it turns out it occurs pretty often in nature. So we call it the natural exponential function. And we'll see lots of places where it pops up. And that's fine. Let's go to the next page. Number 10, Tyler. Meaning? Okay, so new phrase. Compounded continuously. It doesn't mean every week. It doesn't mean every day. It doesn't even mean every second. It means at every moment in time, more often than every second, okay? If you see that key phrase, compounded continuously, then you don't use that formula, you use this one, okay? For any other compounding, you use the top formula. Weekly, daily, quarterly, every second, it's always the top one with the N. But the only time we don't use the top one is if you see what keyword? Continuously. If you see continuously, that top formula becomes the bottom formula. P e to the RT. Some folks try to remember that as PERT. You guys, I don't know if they still make that shampoo, but I think they do. So remember PERT, and that's your formula. So let's see if we can do this number 11. We'll go to Ben. Okay, I'm actually going to we're going to answer a different question first. Monthly instead of continuous compounding. Let's do monthly first, and then we can compare it to the continuous compounding. If we do monthly, is it the first formula or the second one? First one. The only way you get the second is continuous. So let's do the monthly business. So how much is P? 1,000 times 1 plus R over N. R? 0.04. Don't forget it's a decimal. Don't put a 4 up there. You put a 4, you're doing 400%. Divided by, if we're doing monthly compounding, how much is N? It's 12. To the same 12 times T. How many years are we letting the money grow? 10 years. Very carefully type that into the calculator. Before I hit enter, I like to think about what I might expect. Sometimes I can catch some errors that way. Suppose it's just 4% interest. Forget the compounding monthly, just straight 4% interest once at the end of the year. How much money do you get for 1 year's interest? It's $40, right? If you're doing 4% of $1,000, it's $40. Easy enough. We're letting this money grow for 12 years. How much do you gain if you have $40 every year for 12 years? It's $480. Should this number be more or less than the 480 additional? A little more. A little more. You're getting interest more often than just once a year. So I'm expecting something, you know, like $1,000 plus 480, maybe 1,500. Oh, look at 10,000. Don't ruin my, I'm so happy now. I have 10,000 in the bank. What did I do wrong, Connor? I did. I tend to do that. Okay, so we're going to insert parentheses right there. Now, we should get something around 1480, but more than that. Maybe 1,500, I don't know. 1490. That reasonable, it's sad. It's worse than the other one, but it's the right answer. So $1,490.83. Put that here. Oh, real nice trick. If you do second and then enter, and then you can edit. Oh, putting the parentheses in. Yes, I did. Okay, so it used to be that without parentheses. If you just put parentheses right now, what is it going to do? It's going to erase the one. It types over. So we need to use the insert command, which is in yellow. Second, insert. And now it's in insert mode. And I can put parentheses and it moves everything over. Okay, now let's answer the question that was originally asked. Continuous compounding. Top or bottom formula? Bottom one. So we go PERT. 1,000 is still P. E is E. Don't put anything else. It's not a variable that's getting replaced. It's E. It's around 2.7. What is R? 0.04 times what is T? 10 years. This is what we're typing in very carefully. So we're doing 1,000 And then there's this E to the X button on the left-hand side. I like that one. Second E to the. Do I need to put in extra parentheses? It gives it to you. It knows that you might be dumb enough to forget the parentheses, so it puts it. This calculator was designed with me in mind. 0.04 times 10. Parentheses are there. It's taken care of. Another benefit to using the E on the left-hand column instead of the E on the right-hand column. Gives you parentheses. Are we expecting something more or less than $14.90? More. You're not getting interest every month. You're getting it every instant of the day, more often than every second. $14.91. All right. Don't spend it all in one place. So we got about an extra dollar out of that. All right, get a couple of tater tots for that. That's good. All right, questions on that PERT business? So there's a few things you need to know to be successful with this kind of a question. You need to know when to use PERT, what keyword, continuous. You need to know how to write it down in, like with pencil and paper, and you need to know how to type it in. So 1491.82. That's not worth it to you? Not good enough? All right, so if we want something more dramatic, I mean, it does start to separate, but let me do this. Suppose that we went back, we don't need to copy this. Suppose that you had something that wasn't just growing for 10 years, but rather was growing for 50 years, okay? 50 years. In fact, let me go back one more. All right, so here's the original one. So 50 years growing, compounded every month. It's $7,364. That's after 50 years monthly compounding. Now if we do continuous compounding, we just change this to 50 years. Should it be more or less than the 7,300 that we saw? Should be more. This is 50 years continuous versus monthly. All right. You guys are not impressed. It's not $1 anymore. It's $25. It's 25 bucks. Yeah, pretend that those are thousands of dollars. Ah, okay. You guys are just tough to please. Okay, so this is good. All right, what if we go to, oh, one other thing. Does any bank in the world give continuous compounding interest? No, I mean, computers couldn't even handle it, right? I mean, like a computer, no matter how fast it is doing things at discrete moments in time. Like there's no way a computer could deal with giving you a little bit of interest at every moment in time. We can use our formula, and at the end of a year, the computer can tell you exactly how much you have in there. But it can't actually send you like these little parts of a penny at every moment of the day. But this continuous thing, it turns out it's a reasonable assumption for a lot of stuff. What is inflation? Okay, prices of stuff rise. Yes? Like things today generally cost more than they did 20 years ago. Okay, if the prices tomorrow were double what they were today, you go out tomorrow and everything is double what it is now. Is that inflation?
Yes. Prices double every day, that's hyperinflation.
Well, I didn't say every day, I said tomorrow. Okay, so it has to do with income and hopefully your salary is rising as well, kind of keep pace with it. Inflation isn't just a rise in the general prices of things, it's a trend. It's a rise over time. If prices were to double tomorrow, that's not inflation. I don't know what happened, but it's not inflation. Inflation is a gradual, longer term thing. In fact, inflation is generally something so gradual that you can't put your finger on exactly when the prices got higher, right? You could think back to 5 years ago, say, oh, I remember when I used to buy my Hostess cupcakes and they were only this much, but today they're this much. But you can't like pinpoint one moment in your life where Hostess cupcakes went from being inexpensive to kind of a lot now, right? It's a gradual thing. And so, I don't think it would make sense to try to say, okay, let's try to model the prices, all of them go up at the end of the year. Like on January 1st, that's when all the prices go up. They don't change like as like on a scheduled basis like that. It's a gradual thing. It's a long-term kind of gradual process. And so this PERT formula, turns out, is a good formula to use to estimate inflation. Whenever people talk about inflation, they use that. Another place where we use this, suppose that instead of having money growing in a bank, you have a population of ladybugs out in the field here, just behind our school. So what's going to happen to make this population grow? Ladybugs will reproduce, right? Little baby bugs, but baby ladybugs. Okay, and could we use the top formula to maybe estimate how many baby ladybugs are there? The top formula says compounded, like once a month or once a day. Can you predict? All right, on like the 4th of every month, that's when the population is just going to jump up. So there could be a seasonal type thing. My feeling, and I don't know too much about ladybugs, my feeling is that it's more of a gradual type thing. You can't really predict, oh, tomorrow the population will be double what it is today. Probably not. But maybe we can kind of use the second formula here to estimate. The population doesn't increase in like these discrete moments in time. It's kind of more of a gradual, general, unpredictable almost type thing. So lots of stuff in nature uses this PERT thing instead of the top formula up there. All right, let's take a look at stuff not growing but shrinking. We'll go to Joe for 12. Okay, let's pause there. Half-life is a unit of time. It is how long, okay? It is how long it takes for stuff to decay. So where do they use half-lives? Half-lives. Chemistry uses it. What else? Yeah, in medicine. Have you heard of, what's that? Nuclear power has to do with half-lives, yes. Have you heard of carbon dating? We want to find out like how old some dinosaur bone is. Do you just like, do you count the rings like a tree? We can't do that, right? So what do? Well, they use this idea of this half-life business. Turns out that when the dinosaur was alive, there was a predictable percentage of its body that was carbon. I don't know what percentage it is. Let's say dinosaurs were 20% carbon. Then the dinosaur dies, and that 20% doesn't stay 20%. The carbon is no longer being produced by the dinosaur, so the carbon gradually disappears. Now, if the carbon disappears fast, then how much carbon will be in the dinosaur's bone today? Basically nothing. Carbon disappears really slowly, like really slowly. Remember we had the drug filtration thing, and it was 25% going away every hour? It's not anywhere near that for carbon. Carbon decays like it feels like it doesn't decay at all because it takes so long for carbon to disappear. Here's an example. The half-life of carbon-14, that's a particular, I don't know if this is the right word, isotope of carbon? Possibly. Okay. A particular brand of carbon, it has a half-life of 5,730 years. That means that however much carbon is in your body today, 5,730 years after you die, what part of the carbon will still be there? Half of it. It takes 5,730 years for half of the stuff to go away. If I waited another 5,000 years, then how much would you still have? You'd still have half of that. You'd still have 25% of what you have today. If I wait another 500 years, you'd have half of that. You'd still have 12 and a half. Or like 16,000 years into the future, you're still going to have 12.5% of the carbon in your body that you have right now. That's why it's useful, because the carbon takes so long to disappear that there's still some of it in the dinosaur bone, a detectable amount in the dinosaur bone. Okay, so here's a formula. It says M of T. M is going to represent the mass of the substance, like how many grams of carbon are still in the dinosaur bone. That's what M represents. Of course, it's a function of T. As time passes, the amount of stuff, the amount of carbon disappears. So it's M0. That's the, what do you think the 0 represents? The 0 time, the initial amount of stuff, the initial number of grams of carbon, that's M0. Then there's a half because we're doing a half-life. Then there's T. T is how many years pass. And then there's H. And H is the half-life. And I want us to make a connection here. You guys remember the other day we had this formula, 1,000.75 to the T divided by 4. We did that for the drug filtration example. Started with 1,000 milligrams of the drug. 25% of it disappeared every hour, so every 4 hours. So 75% of it was still there. That's the 0.75. But then it wasn't just to the T. Why is it T over 4? Why was there a 4 in this problem? Every 4 hours it happened. So that T over H is kind of like the T over 4. It's not every year that the amount of stuff gets cut in half. It's every 5,700 years. You're going to have to take that T and divide it by 57 in the formula. All right, let's see if we can try 13. Serge. Okay, let's see if we can use the equation and then we'll answer some other stuff. Okay, it says today we have 59% of what we originally had. Okay, I don't know what we originally had, but it was called M0. And then there's a half. And then there's a T, which I don't know how long this bone has been, or this mummy, this cloth has been in existence, but I do know what the H is. How much is H for carbon 14? 5,730. So that's the right-hand side. The left-hand side represents how much stuff, how much carbon 14 is still there today. Now again, I don't know how much it is, but I know it's 59% of what it used to be. So I'd really like to put a 59% of what it used to be here. How do I write that symbolically? 59%. First, how do you write 59% in an equation? 0.59. Okay, so we hardly ever write 59% as 59. Okay, I like 0.59. It's 59% of whatever you started with. The M0, isn't that the name? I don't know what I started with, but I know it was called M0. So 0.59 M0 is 59% of what we started with. So that's the equation we're trying to solve. You have M0 that you began with. Currently, you have 59% of it. What's the first thing you can do to simplify this equation? Divide everything by M0, and all of a sudden, those things go away. So we go 0.59 equals 1/2 T over 5,730. And in fact, if you don't like that 0.59 M0, there is a cheesy way to just write this equation. Suppose that we started with 1 gram of carbon 14. Where does the 1 go in the formula? Right there where the M0 used to be. And if you started with 1 gram and you have 59% left, then how many grams do you have left? 0.59 grams. Okay, so I mean, you get the same equation by, I call it cheesy. I don't know. I mean, I don't know it's 1, but the M0s disappear no matter what happens. So ultimately we get that. I'm trying to solve this equation. Where is the variable? It's in the exponent. We need this technique that we don't have. It's called logarithms. We're getting to it right after the test. So for right now, the only way to solve that equation is by graphing both sides of the equation. We'll do that momentarily. Before we do, can you guys talk to your neighbors and estimate how many years will it take before we get from 1 gram of stuff to 0.59 grams of stuff? 10 years, 1,000 years, 10,000 years, 100,000 years, just ballpark. Don't do any calculations. Just think about the numbers and talk to your neighbors. Okay, what do we think? Roughly how long? Around 5,000 years, that's one guess. Other guesses? 5,200, that is quite close to 5,000. Other guesses? Around 5,000? I'm sorry, around 5,002. Very particular. Okay, how do we know? Well, if we waited 5,730 years, how much stuff would still be there? 50%. Right, 50% would be there if you wait exactly 1 half-life. But we didn't quite get to 50%. We still have 59%. We have more than the 50%. So yeah, absolutely. It's going to take a little less than that 5,700 years. Okay, so let's see if we can graph this thing on the calculator. Y equals. Okay, so we're going to carefully type in the right-hand side of my equation. So we're going 0.5 or 1/2. To the, what do I put up there? x over 5730, right? I don't have t, we have x. Matt wonders if we need parentheses. Do we need parentheses? Does the calculator know that whole thing is an exponent? Nope. Parentheses there. What's the second thing we're going to graph? 0.59, the left-hand side. Now, I'm giving you a big old clue right here with the window. I'm telling you use this window right here. So let's use that window right there. So we'll go into Windows. So the first three numbers are the X numbers. So I'm saying 0 to 50,000. How did I come up with 50,000? Oh, that's the number of years. That's okay. Yeah, let's do that. Okay, so we're going 0 to 50,000. And then X scale is how often you're going to get a hash mark. So we'll say every 10,000 years. And then for the Y's, we'll use the other numbers, 0 to 0.7. My calculator is not working for me. Okay, sorry about that. We'll try it again. So we said 0.5 raised to the x over 5730. And then this was a 0.59, and then the window we had was 0 to 50,000. And then 0 to 0.7, and what was the scale there? 0.01. Okay, so we type all that stuff in. That thing right there is our exponential decay. It's our stuff getting cut in half every 5,000 years. Every 5,000 years it gets cut in half. And then that horizontal line is up there at 0.59. So when do you have 59%? It's when those two things intersect each other. So to find the intersection, we do second calc. And then number 5. And this is the best part. You just hit enter 3 times. And it gives us our answer. You guys had said something around 5,000 years. 4361. 5,000 is a good guess. Questions on that one? Okay. So the homework is there. And in the last 3.5 minutes or so, I just want to talk a little bit about the test. So if we go back a few pages, can you guys jump to page 49? Okay. Again, when is the test? Friday. Wednesday is our review day. We just finished the end of the new material for the test. At the bottom of page 49, you see this study guide. There's a very detailed list of the stuff that I would like you to be able to do to be successfully prepared for that test on Friday. Go to the next page. The list continues. Down here, it tells you some of the resources you can bring in. Graphing calculator, 1-page sheet of notes. I will bring the calculators in for people to borrow on Friday. Then there's some extra problems. None of these were homework, so you haven't done them. But if you want more problems to do, there's a good list of stuff from your textbook. And then again, finally, the sample test problems down here at the bottom. And just want to remind you that, like before, I made videos and I put them on YouTube of all of these things, me going through all of these. So if, for example, you want to know how to do number 2, or at least you want to get a sense of how I did number 2, I type in, here's the syntax, well, it's that. There. 107 sample test 3, problem 2. If you type that in, mine will be the first hit because my YouTube channel is so popular. Also, nobody else has a title that's that. So if you click on that, you will see me and you will hear me going through that problem right there, which is the same as that problem right there. Okay, questions on the resource? Okay, we will end a minute and a half early. Don't say I never did anything nice for you. See you guys Wednesday.